Hello, my name is Martin Dockendorff. I'm a PhD student at the Central European University, and today I'm going to present to you some of the findings from an ongoing project titled Understanding Distal Goals from Proximal Communicative Actions. How do people use communication to achieve coordination? To motivate an answer to this question, consider the following situation where three friends are playing frisbee together. One of them, the one in the middle here, wishes to quickly tell his friends that he is ready to catch the approaching disc and then pass it to his friend on the right. One quick way of doing this would be for him to move his body and hands in an exaggerated manner. A manner that will make it obvious to his two friends that he will both catch the disc and then pass it on to the right. Know that by moving his body and hands like this, he can achieve two goals simultaneously. The instrumental goal of catching the disc and passing it on to his friend, and the communicative social goal of providing information to his friends about his future actions. More importantly, these movements fulfill these two goals by means of exaggerations or modulations in certain kinematic features of the movement itself. This general capacity to provide useful information about instrumental goals by exaggerating the movements used to achieve those goals has been termed sensorimotor communication. We now know from previous research on sensorimotor communication that observers can recognize and understand a wide range of communicative modulations in instrumental actions that convey information about someone's proximal, more immediate goals. So for example, people can predict whether someone will reach for an object located to the right or left by looking at the exaggerations in the initial trajectory of a hand movement, or people can understand whether an agent will grasp an object from the upper or lower part by looking at the exaggerations in the height of the wrist. Or finally, they can predict whether a person will move closer or further by looking at the exaggeration in amplitude of their arm movements. All these findings show that within the context of a joint action, sensorimotor communication plays the role of a coordination smoother, that is, a behavioral strategy whereby people make their actions easier to predict, which in turn facilitates coordination. But what about more distal goals? Let's consider again our frisbee example. Here, thanks to these exaggerated movements, the two observing friends can understand and predict what their friend in the middle is about to do, and so they can derive information about his proximal goal, namely that he's about to catch the disc. But, as I said at the beginning, this interpretation of the movement normally doesn't need to stop there. It is actually very likely that based on his exaggerated movements, the two observers here will try to predict what their friend will do after he receives the disc, and by doing that derive his more distal goal, a goal that follows temporally his more proximal goal. In this case, his more distal goal is that he will pass the disc to his friend on the right. Predicting such distal goals will then allow the two friends to adapt their behavior accordingly. The one on the left can relax and wait for his turn, while the one on the right can prepare to receive the disc. Again, previous research has shown that movements can be affected by distal goals. In the motor control literature, previous studies looking at two-step action sequences have shown that distal goals can have a strong modulating effect on certain kinematic features of early action components, such as the total duration or peak velocity of two-step aiming movements, or the shape of the hand or fingers in a two-step grasping movement. Also, research has shown that observers can use these early variations in movement kinematics to predict someone else's distal goals, such as when people observe others picking and placing a dowel. Drawing on these two lines of research on sensorimotor communication on the one hand and on action understanding of distal goals on the other, we asked the following two research questions. First, can people interpret early modulations of goal-directed movements in terms of their distal goals, that is, goals that are temporally separated from the achievement of a more proximate goal? And second, how will exaggerations contribute to the understanding and interpretation of these early modulations of goal-directed movements? To address these questions, we created an online observation study where participants saw animations of a box being delivered towards one of two target locations. In one condition, participants saw the box being delivered along a black line towards either a near or far target. Participants saw the box moving at different velocities, which differ depending on the target location. Movements going to the near target were slower than the ones going to the far target, as you can see in the velocity profiles here. Note that this difference in peak velocity between movements directed towards different target locations is consistent with a finding from previous studies showing that far targets are reached with higher peak velocity than near targets. We then exaggerated these movements by adding one standard deviation to the peak velocity of the normal far movement, or subtracting 1 standard deviation from the peak velocity of the normal near movement. And then we repeated the same procedure, but this time with 2 standard deviations. This meant that we had a total of 6 movements, 2 normal ones, 2 exaggerated with 1 standard deviation, and 2 exaggerated with 2 standard deviations. Now, since the box in this condition moved along the black line towards either the near or far target location, the proximal goal of sliding the box and the more distal goal of placing the box within one of the target locations fully overlap. As a consequence, we labeled this condition the full overlap condition. We compared this condition to one where participants saw the box moving towards a gray area in the middle of the screen, where it stopped for a few seconds before disappearing and then reappearing within one of the 2 target locations. The movements participants saw in this condition were taken directly from the full overlap condition, but we reshaped them so that their endpoints would all converge towards the middle of the screen, this gray area in the middle. This reshaping of the movements retained most kinematic features of the original movements from the full overlap condition, but eliminated the differences in movement distance such that all movements had now the same endpoint. Since the box in this condition only moved along the black line towards the middle of the screen and then was automatically delivered towards one of the target locations, the proximal goal of sliding the box and the more distal goal of placing the box within one of the targets did not overlap. As a consequence, we labeled this condition the no overlap condition. At the beginning of the experiment, participants were randomly allocated to either the full overlap or the no overlap condition and were presented with the 2 normal movements in a randomized order. In the full overlap condition, they saw the box being moved towards one of the 2 targets, whereas in the no overlap condition, they saw the box being moved towards this gray area in the middle, where it stopped for a few seconds, disappeared, and then reappeared within one of the target locations. We then presented participants with a cover-up story and told them that the movements they would see had been collected from a previous experiment in which we asked participants to move this box to one of the green locations. But more importantly, we told them that the movements we collected had been produced by this previous participant in a way that would help potential observers understand to which green location they were moving the box. This was important not only because we wanted to make it explicit to participants that these movements were communicative, but also because during the actual trials, participants were not able to see the target locations, as these were covered with a rectangular black occluder, as you can see here. So, during the experimental trials, participants saw the box being moved either towards the occluded targets in the full overlap condition or towards the middle target in the no overlap condition, where it stopped for a few moments and then disappeared. At the end of each trial, participants were asked to select the location they thought the box had been moved by either pressing the N key for near or the F key for far. Our design therefore consisted of a mixed factorial design with 1 between subject factor or 2 overlap conditions, and a within subject factor, the 3 movements, normal, exaggerated with 1 standard deviation, or exaggerated with 2 standard deviations. Participants were presented with 36 trials in total, divided in 6 blocks, and we recruited 25 participants per condition on the online testing platform Testable. So, what did we find? First of all, we wanted to see whether participants interpret the different movements consistently throughout the experiment. To do so, we calculated consistency scores for each individual participant. These consistency scores were the absolute difference between the total number of predicted mappings and the total number of inverse mappings per participant. These 2 mappings correspond to associations between key responses on the one hand and movement velocities on the other. We call the far to fast and near to slow associations predicted because these associations are consistent with the finding that far locations are reached with higher peak velocity, so faster movements, compared to near locations. Inverse mappings correspond to a reversal of this association between locations and movements. More importantly, our consistency scores could range from 0, which meant that participants had created random associations between movements and target locations, to 12, which meant that the participants were fully consistent in their mappings. We grouped consistency scores into the 3 different degrees of exaggeration, which you can see on the x-axis here. The left panel corresponds to the full overlap condition, the right panel to the no overlap condition. As you can see, in both conditions, participants are able to create consistent mappings between movements and target locations, even when the movements are normal. And as we predicted, we found that the more exaggerated the movements, the more consistent are participants in their mappings in both conditions. But then we also wanted to know how specifically did participants map the movements onto the targets? What kind of mapping did they use? To address this question, we calculated mapping scores, which are very similar to consistency scores, but this time the difference between predicted and inverse mappings is not the absolute difference, but the sign difference, which meant that mapping scores could now range from -12, meaning fully inverse mappings between the target locations and the movements, and +12, meaning fully predicted mappings between target locations and movements. A mapping score of 0 means no preference towards either mapping. We found that in the full overlap condition, participants were more likely to produce predicted mappings, that is, to map fast movements to far targets and slow movements to near targets. In the no overlap condition, however, we found that as a group, participants did not have a preference towards any of the two mapping directions, as indicated by the non-significant differences in the distribution of mapping scores from 0. Interestingly, when movements were very exaggerated in that condition, so 2 standard deviations, some participants mapped the movements in the predicted manner, while others inversed the mapping, thus yielding a bimodal distribution of mapping scores. To sum up, we showed in experiment 1 that participants can produce consistent mappings between the velocity of different movements and target location. We also showed that their mappings tend to become more consistent when movements become more exaggerated. Regarding the direction of these mappings, when the proximal and distal goals of the movement overlap, as in the full overlap condition, all participants produce predicted mappings, that is, mappings where fast movements are mapped onto far targets and slow movements onto near targets. However, we also found that when the proximal and distal goals of the movement did not overlap, as in the no overlap condition, a group of participants failed to display a clear preference towards either of the two mappings. Note, however, that the movements participants saw in the no overlap condition were originally taken from the full overlap condition and reshaped so that they would all converge towards the middle of the screen. One possibility is that this reshaping of the movements made the task harder for participants in the no overlap condition, since movements may have been harder to discriminate perceptually in this condition. To address this question, we conducted experiment 2, which was identical to experiment 1, but differing that participants never saw the targets behind the occluder during familiarization, and after watching the movements, they were simply asked whether they thought the movement they had just seen was a slow or a fast movement. With experiment 2, we can ask the question, can participants perceptually discriminate between the different movement velocities? To address this question, we computed discriminability scores for each participant, similar to mapping scores in that they range from -12 to +12, where -12 means fully incorrect answers, while +12 means fully correct answers. Here, we found that in both conditions, participants can correctly discriminate movements, as indicated by their high discriminability scores, and as expected, more exaggerated movements are more easily discriminated. We then compare the mapping scores from experiment 1 to the discriminability scores from experiment 2, and ask whether participants' capacity to discriminate the movements differ from their capacity to map the movements to locations. The upper panel shows the mapping scores from experiment 1, and the lower panel the discriminability scores from experiment 2. In the full overlap condition, we didn't find a difference in the pattern of results between the scores of experiment 1 and 2. In the no overlap condition, however, we did find a difference between the mapping scores from experiment 1 and the discriminability scores from experiment 2, suggesting that our findings from experiment 1 are not due to difficulties in discriminating perceptually the velocity of the movements. In summary, our findings of experiment 1 show that people can interpret proximal communicative actions in terms of their distal goals. And consistent with previous findings on sensorimotor communication, we show that they can do this by relying on exaggerations in the velocity of the movements. However, we also show that the separation between a proximal and a distal goal introduces variability in the way participants map the movements to the locations. We are currently conducting new experiments looking more closely at the potential factors that contribute to these changes in interpretation and mappings. Before ending, let me thank my two supervisors, Günther Knoblich and Cordula Vesper, and my colleague Laura Schmidt for their support and guidance throughout this project. Also, let me acknowledge the European Research Council and CEU for funding this research. Thank you.